You didn't get called, and your name is?
Camp Schmidt. Okay. Stephanie.
Where are you on there?
It's just a V, sorry.
Oh, okay.
Yeah, I was.
Well, I didn't count your absence, so I must have seen you back there. Okay, have a seat. Class begins. If you have something to say, do it on your own time after class. We've already spent all the time. That's 5 minutes on you. I know, horrible. All right. Once you get through with solving for the end moments on these structures, you got to know what to do with them. Generally speaking, you'll have shears on the beam. Shear, say A to B. I put them on here any direction you like. They probably won't come out right anyway. And you have a shear BC. And using the slope deflection method, you will have solved for you will have solved for theta sub AB, but you will plug it back into your equation and it will give you the moment AB. Yeah, I can. Goodness, wonder what happened. Okay. Open Sesame. Yeah, I don't know what went wrong there. Okay, thank you. And you will have solved for theta sub BA, and you will be getting a corresponding moment on end B looking back towards end A. Now then the question is, what do you do with it now that you've found it? To draw a shear in a moment diagram, you have to know the shears on the structure. So the first thing we would do would be to solve for the shears. Let me move this theta AB out of the way. How would you solve for the shears on a structure like that? Booth. See, you said you weren't loved. Not the case. How would you solve for the shears on that chunk of steel? Thank you. Take the sum of the moments about either end would be right. Any point would also be correct. The only thing is, if you sum moments about this point, both the shears would appear in the equation. Then you'd have to sum moments about some other point and get an independent equation and solve them simultaneously. It makes a lot more sense to sum moments, for example, about A is equal to 0 is equal to minus 30 kips times his moment arm, 8 feet, minus 2 kips per foot, times my moment arm's wrong, 6, thank you, times 10, times the moment arms, 14 and 5, 19. Plus the shear at BC times his moment arm, 18, 24. And then the external moments on the end would say minus 60. And then minus 20. Now, if you're saying, whoa, why did you not put a moment arm in there? But you figured that out, right? This guy here needs a moment arm to turn the force into a moment. This uniform load needs a moment arm to turn it into a moment. This guy already is a moment. He even has the proper units. So he just gets thrown in. You say, would the answer not change if the 60 was applied here? The answer for the shears would not change. And then you'll solve for V sub BA if you have a calculator. I'm not going to, and I don't even care that you do it. There's the shear at B, looking back. Yeah, I like that name better. B back to A, because we usually work these things in a chunk of steel between reactions. Now then, let's say that you have another, I'm going to just put a box around it like we know the answer for that one. Now then, let's say that you had another piece of steel extending on down here, and it had a bending moment of 30, and this is down here. There's a joint in between these two, and it has a load on it. Let me just make the loads a little simpler. 60 kips. And on this end of the moment, you found that the answer went that way, and on this end of the answer, you found it went that way. And this was a 50. And this is A, B, and this is B, C. And this dimension was 4 feet and 8 feet. And that's all you would really see, because that's all the method gives you. It just gives you the moments at the ends of these members, plus or minus, depending on if they really go clockwise on the end of the member or count. Hello, Getman. Doing great. Better that you're here.
It just got beamed in.
It got beamed in. All right. Where's Scotty? On this end, there's a reaction. That's the shear at B looking towards C. And on this end is the shear at C looking back towards B. And you would do exactly the same thing. You would, for example, some moments about point B is equal to 0 is equal to blah, 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 blah. And you would solve, since I'm summing moments about B, you would say V sub CB is equal to, and you'd put a box around it. Now then, looking at that, I can tell you, since the moment at B looking back towards A is not the same as the moment at B looking towards C, this must have come out of something that looks like this. And this is A, and it was supported somehow, who knows. And this was B, and this was C, and this was D. Because otherwise, if this was just a single member went all the way across there, the moment on the left-hand side of the joint would have to equal to the moment on the right-hand side of the joint. But I can tell you what's going on. Here is that joint. On the right end of the piece of steel is a clockwise 20. On the left end of the joint is a counterclockwise 20.
Dr. Lara,
Yes, sir.
question. For that joint, the moment on the piece facing down.
Wait. This piece, this guy here?
Yeah, that joint. There,
Okay.
that T-tip joint. Whatever the moment is on the left-hand side, it's equal to the moment on the right-hand side.
It would normally be.
But it's not. But the moment in the vertical piece is 0, wouldn't it?
Don't know. Let's see.
But it doesn't have to equal the other two.
Well, I'm not sure what you mean by equal to, but I'll tell you this. You see that little chunk of steel? Extracted from the frame after we finished with slope deflection, he's never been discussed. He has to sit still. There is no question about that.
What, like if you have just like an L joint, then the moment on, at the corner of the top part will be equal to the moment here?
In general, but not necessarily. Remind me and I'll show you one like that. Does everybody agree that the answer you found was clockwise on this end is 20? That was, in effect, given. Therefore, it's counterclockwise on that joint. On this member BC, the final answer for the slope deflection method presented to you with a box around it and a bow on it, 30 kip feet counterclockwise on the piece of steel member. Therefore, this number right here is 30 kip feet clockwise on the joint between those two members. That has to sit still. If that number's not equal to that number, then there's got to be somebody else coming in. if that was equal to that number, there could still be somebody coming in with no moment in it. But that's not the case here. Because if you, now let me tell you who else is working on this joint. There's an axial force, and there's an axial force, and there's a shear, and there's an axial force, and there's a shear, and there's a shear. Now I just threw those arrowheads on there. I have no idea which way they truly go. It's probably possible to make them actually come out that way, but I'm not going to worry about it. This guy's name is the force in member Baker Charlie. This is the force in member Alpha Baker. This is the force in member Dog Baker. This is the shear in member Dog looking down. Hang on a second. This is the force at joint B looking down to joint D. This is the shear at the top of member B down to D. This is the shear BC. This is the moment BC. That's what we put in our initial slope deflection set of equations. And what is this guy right here? There we go. What is this shear right here? Yeah, what's his name? This one right here. The one at joint B, AB. No. But it's not your fault that it's not AB. It's my fault it's AB because you saw an AB there, and that's really not a good name for him. Because he's on end B looking back towards A. So now you could probably give me a more accurate answer. BA. I mean, I don't care. You can call them anything you want to. Call them dogs and cats and kangaroos. But, you know, if they got nice names like that that follow some kind of a naming convention, it makes a lot more sense. All right. Therefore, the one thing I don't have left here is this moment right here, and his name is the moment up at point B looking down towards D. And I can tell you how big he has to be, whether or not you got it from slope deflection equations or whether you get it from statics. The sum of the moments about joint B must equal to 0. And all of these other axial forces and shears and everything, they don't do a thing. They don't make any never minds at all because they have no moment arms. This guy has no moment arm. It goes right through point B. This shear looks like he's got a moment arm, but only because I drew it big enough for you to see. He has no moment arm. He has no moment arm. And therefore, you would say minus 20 plus 30 plus the moment at the joint looking down at the other end of the member is equal to 0. And therefore, this number right here is a minus 10.
Why are you summing moments in that direction?
Because I like things to sit still, because when they don't sit still, people die.
Oh, I mean, is there a particular reason you're summing them in the opposite direction?
Well, I don't know about opposite. In other words, this is a statics situation, and so I sum moments about this point to solve for this unknown.
Yeah, but I would have summed them in the other direction. Yeah.
That's your choice. That's your choice. I was kind of raised on this as a statics sign convention. But no, half the people hate it. The other half love
So
it.
in that case, you did the opposite.
Well, I'm not sure what you're saying.
Well, that should be a plus 20. The way it's
Oh, I'm sorry. Yeah, you're right. So I don't always do my own sign convention. The sign convention is okay. The sign convention is acceptable. All you got to do is be consistent, and you still get the same answer. So thank you. Plus 20 minus 30 minus m sub that's equal to 0, and therefore m sub Baker Dog is a minus 30 using my sign convention in a minus 10 instead of hers. I'm sorry?
Falling off.
Falling off? Oh man, I fell off long ago. Question now is what's left? All right, now let's talk briefly about the joint that you asked. If you put 20 on this side, will you always get 20 out on this side? Well, evidently the answer is no. And therefore, guess what someone did on the outside of your frame? On the outside of the frame, he stood on the hillside, he had a torque wrench, and he did this on the outside of the structure. So, generally speaking, yes, anything that comes in on this side of the joint comes out on that side of the joint. But if there's any concentrated moments at those points, they have to be accounted for.
So if there are no concentrated moments,
Then
you have like a T.
then, well, now then if you had a T thing, here, see here, there was no outside concentrated moments, but they still did not flow 20 to 20 because this guy, in effect, was on the outside coming into the joint. The final thing to do is always clear and obvious and shouldn't be in question. Put the joint in equilibrium. All right. Now then, you have a problem in your book. I have modified it so that you'll still have the problem in the book to work with, but it looks very similar to this one. It is and you can look it up, it's on page 496, just so you can see, the picture. I think I left the dimensions alone. It's a 15-foot, 12-foot, 18-foot, changed into inches. His has a 6-skip load on it. It has no uniform load. I wanted some uniform load. I believe his is fixed and fixed. I put mine fixed and pinned. So there'll be some difference in the equations, but you ought to be able to take his then and see if you know what he's doing. I also didn't bother with EI changing in each member. I just left it 240 in every member. There's a good chance you'll see some mistakes in this. Holler, I'll change them. Now when you press on the structure, it deforms the structure in some shape. We are neglecting axial forces and axial distortions and deformations. I would say this, a member that's 12 feet tall with a 6-skip load on it probably going to deflect probably a ½ inch, maybe an inch. And with the axial load on the floor, it will probably compress 0.002 inches. The reason is because your deformation for axial is PL over AE, and that's a monstrous number. And the deflections are usually far greater in magnitude than the compression. So I'm going to tell you that I'm going to omit axial movement up and down. I'm not going to consider it an unknown. And I'm going to tell you that the bending of this member pushes this to the right an amount. The deflection at B, if you point your eyeballs back towards A. I'm also going to tell you that this end of the member moves to the right and that delta CD is going to be the same as delta BA because I am going to exclude any axial compression distortion of this horizontal member. You don't have to. You could say it's different and you could include the term PL over AE. The truth is you won't get any different for any of the answers. That's just too small of a distortion to worry about. So I'm going to tell you that in the equations they will call for delta BA, and you stick it in there. But delta BA is equal to delta CD, and we could just call it a single unknown delta. And it is unknown. If I knew what it was, I'd be further down the road. How far down the road would I be? Wake up. No. That's the old ploy. The guy's sleeping, sound asleep, making noises. They say, wake up, and he looks around him. Who's he talking to? No. Theta at A, I don't like that name. Theta at A, looking up towards B, is the rotation of joint A. And in the equations, we'll just change it to theta sub A. Let me show you a bigger picture of the thetas. Here's the distorted structure. Here is your theta sub A, right here. It is equal to 0 because it's fixed. Theta at B, looking down towards A, is this angle right here. But because this 90-degree angle remains 90 degrees, then theta BC is the same value. There's theta BC, which, for all I care, you can just start calling it theta sub B. The equation won't call for theta B. The equation will call for theta BC when you're working with this guy. He'll call for theta BA, BC is this one. He'll call for theta BA when you're working with this member. But they're both the same. By the same token, this theta CB can just be called theta C. And this theta down on the bottom, that can just be called theta at D. But you have to know when the equation calls for the angle, you know what to replace it with.
Really quick, why is your delta C, like your deflection of C, why is it delta CD?
May be wrong. Let me check it.
Not on that page, on the other.
On the other page, all right. Delta CD
On the drawing.
on the drawing. You mean this angle here?
Yeah, why is it CD? Why isn't it?
Well, I don't have theta shown on this one. There just wasn't any room. But now then this delta here is how far this member right here moved to the right on its end. So it's the deflection at point C looking down towards end D. Now, for example, you see how far this one moved up and down, and the answer is none. Down, 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 up, 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 down, up, down, up, down, I don't know. You see how this length of this member is unchanged because we're excluding axial forces? That means that the motion of this member from here up and down to here is 0. So there's actually another delta right here. His name would be the deflection at end D, looking back towards point B, and it happens to be 0. All right, so just as a quick summary of things we do know, we know that these deltas are equal. We know theta A, since it's fixed, is 0. We know that theta sub B, take your choice of which one of these you want, whichever member you're working on. We don't know what it is. It's something, but it's unknown. Theta at C is unknown, and theta at D is unknown. Those are our unknowns. Those are the things we're going to be solving for. There's 1, I know that one, 2, 3, 4. You're going to have to give me 4 solid pieces of information to solve for those angles or the moments associated with them. Generally speaking, here's the moments that we're going to be using. Here's member AB. We show an unknown moment on end A looking towards B, and an unknown moment at B looking towards end A. We show them clockwise on the member because we got to show them some way, and so somebody, long before I got into the game, and before you did, said, let's call positive clockwise on the ends of the members. They do that everywhere, on every member. That has the result of, on every joint, you see the unknowns listed as counterclockwise. Now then, we start generating blindly. We already did all the work when we worked out how much moment there is on a piece of steel. The amount of moment on any piece of distorted steel like this one is equal to 2EI over L times 2 times the rotation of the joint on the near end plus 1 times the rotation in radians on the far end minus 3 times the deformation between the two ends over L 3 times, and then there's a fixed end moment. In other words, like in this case, because this load's on the member, if you just fix the ends of the member, you'll be putting some moment in the piece of steel on these ends. And here they are. First, I don't know if I really need the picture or not. M sub AB is equal to 2EI over L. The only thing you see, I stuck 144 in there because that's how long member AB is, times 2 times this angle theta AB. I don't know what that angle is. I'll worry about it later. Plus the theta on the far end, B looking back towards A. Minus 3 times if there's any relative displacement between the two ends of the members, divided by the length of the member plus fixed end moment. Now here is your delta. If you look at the member as a horizontal member, and if you're working from A to B, and if you think the thing deflects down, then delta sub BA is a positive number. That's the sign convention we've been using. If you say, well, I hadn't planned on working with delta BA, I actually intended to work on this end with delta AB. How much deflection there is on end A relative to a measuring line through point B. You get the same answer. Since this went clockwise, it's called a plus. Since this is clockwise, it's called a plus. If, for example, you had a structure that looked like this, and it distorted like this, you would be calling this delta positive, and you would be calling this delta negative. See how this one right here, the end rotated clockwise with respect to that end? But you see how on this one it rotated counterclockwise with respect to the end? That's how you could get some plus deltas and how you could get some minus deltas. All right, so that's how far we got. Now I'm going to plug real numbers in here. Here's a 2EI over L is times 2 theta AB. I'm just going to replace that with a theta sub A in a minute. Plus theta BA, I'm just going to put in a theta B, minus 3 delta, 3 over 144 times delta, plus, now I'm going to go get the fixed end moments. The fixed end moments, you look at the structure, you tell me that if this was a fixed beam, how much load is on it and how much moments caused at the ends. There is no load on it. Since there's no load on it, you have no fixed end moments. So I put a 0 in that slot. I don't know why, but I don't know. I guess I did somewhere, because someplace along the line I get the privilege of putting what here? 0. There's no rotation at that end. Now that is a person standing here looking this way. That's equation 1. Now then he walks. See him walking. Now he's on this end, and he's looking this way. And that's equation 2. Equation 2 says, other end, b to a, is equal to 2ei over same 144 times 2 times the theta on the near end, looking back towards a, plus theta on the other end, minus 3 over 144 times delta, and there's no fixed end moment. And again, I guess later on, I know I did it, couldn't solve for it otherwise. Theta sub A gets to be, you get the privilege of setting that to 0 because you know it is fixed at that point on the frame. All right. Mr. Getman. This is you right there, and you're looking this way. And do you have any notes with you?
No.
Do you remember any of this stuff? Can you remember this? I mean, I don't have much room to show too much more stuff. There's the equation. And there's the picture. Maybe I can actually get them all on here. And you're going to be doing this thing from B to C. You ready? M sub BC is equal to,
2ei.
all right, 2ei. That L there was 180 inches. All right. All right, on to 2.
Theta BC.
That's good. Which we will be replacing with just a plain old theta b, which we will be setting equal to 0? No, we won't, because we don't know what it is, and it probably isn't 0. All right, plus theta c back to b, good. Whoa, wait. Now, how about our 3 delta end near to C divided by 180. All right, parentheses. Wait a minute. You're getting.
Plus, whatever that moment is at that end.
That is correct. And what's more, due to uniform loads on top of fixed beams, there will be some concentrated moment on the end due to that load that'll be right under your feet. Got a book?
No.
Can you borrow a book?
Borrow a book.
Is there a book within 30 feet? 40 feet?
Textbook?
Textbook. No, what did you think I meant? Holy Bible?
Any old book.
Because some of these guys don't have a prayer.
What am I doing?
You're looking in the, I forget where they're at.
Fixed end moment.
Fixed in moments. They're either in the front or the back.
Front.
All right, good. One of these guys.
Is it negative? Oh yeah, it's negative 1 times 180 squared over 12.
Okay, that's that 1 kip per foot thing. That's the load. Times what?
180 squared.
180 inches. Quantity squared. Divided by 12. The 12 isn't squared, I take it.
No.
So it's WL squared over 12.
Yeah.
Good. And then it's a minus because it is exerted on the frame. Thank you. Because it is exerted on the frame this way, and to keep these ends coming straight out of the wall, you will have to do that to the end, and that is not a positive clockwise moment, and therefore it's entered as a negative number into the equations. Now, if you can do that, you're okay. You can go back to texting or whatever, but if you can't do that, you got problems.
Gotcha.
No, don't do that. Just keep it or hang on to it, or all right. All right, now let me see if I like what he did. He did, in effect, m sub bc is equal to 2ei over 180 times 2 theta bc, which he's going to trade for a theta b when things get tough, plus theta cb minus 3 times the delta from b to c divided by 180. And fixed end moment is minus 1/12 180 squared over 12. That's exactly right.
You scared him off, Larry.
All right. Now then.
He was talking about me.
Now let me see about that delta BC thing. How much in this structure does point, shut up, must be Pauly. How much does this point move down with respect to that point?
None.
That's correct, none at all, because this thing didn't move any down. You say, well, if it moved over, it had to move down a little, not enough that I care about it. And the same way with this one. Therefore, later on, we will get the privilege of putting delta BC equal to 0. They really shouldn't permit parking out there. All right. And here I did plug in some of those numbers. So 2ei over 180, there's 2 theta sub b, and I did put the 0 in here, and I cranked out the 1/12 of 180 squared over 12. Incidentally, you and I put a 1. We weren't careful with our units because that's 1 kip per foot, and we've been working in inches, so you want to be careful with your units. So it's 1/12 of a kip per inch. Then we do the same thing, standing at C and looking back towards B. As you might imagine, the equation looks exactly the same. The C and the B are reversed. The C and the B are reversed. The C and the B are reversed. The delta is still 0, and the fixed end moment on that end, according to the book, is a plus. That's why he wrote them with those signs in there to emphasize what to put in these equations. But the reason it's a plus is because here's the load pushing down on the structure. It would like to deform like a simply supported beam, but that's not fixed on this end, and therefore you'd have to do this on that end we already discussed, and this on the other end. This end here, that is a positive application of a moment to keep the beam in a fixed configuration. That's why it's a plus. Then we write m sub cd. Here's m sub c down to d. Same idea. M sub cd is equal to 2ei. It's got a new length. cd dc. Now then, this number won't be 0. This number delta cd will be the same as this number b. Same as this number. Delta AB. I really didn't mean to put anything in there just yet. BA. This number right here, delta CD, will be the same as delta AB. The reason being, when this moves to the right, this member is inextensible, no change in length, and therefore this deflection will be the same as that deflection. And here we'll put that in as a known number. We don't know its value, but we know they're equal. And then you get down at the bottom and you do the same thing. You write the equation from D up to C. There are no fixed end moments because on this member CD there are no loads in the middle of the member, and therefore you don't have any fixed end moments. So we got 6 equations there to tinker with. Here are things that we know. Number 1, in equation 1, theta A is equal to 0. That's this angle right here. It's fixed. I do not know theta B, so I can't give you a number like 0 or 1 or 3. I don't know this rotation, and I don't know this rotation. The problem in your book, this was fixed. He'll tell you theta D in his problem is 0. Mine, I don't know. Here's what else I do know. I've got a free body of this joint. Here are all the forces acting on it that could be there. First, there are some answers from slope deflection, which we haven't yet obtained, but we're working towards it. There's a clockwise moment on the member, unknown, causing a counterclockwise moment on the joint. Same way here. Here's that joint. It's a piece of steel. Got 6 kips on it. There's your moment BC in your slope deflection equations. There's your moment BA. There's also an axial force and a shear, and an axial force and a shear. They're all unknown. However, I can tell you one thing, a free body of the joint would give you equations, some forces horizontals equal 0, some forces vertical equal 0. The one I'm really interested in is that the sum of the moments about point B is 0. That says that M sub BA positive plus M sub BC, by my sign convention, positive equals 0. But this is equation 2. There it is, BA. And this is equation 3. BC. BC. And that says that equation 2 plus equation 3 added together is equal to 0. That's a piece of information. That's something that helps you solve for the forces and the thetas on this frame. Then I can do the same thing for free body of joint C. Here are the moments on the frame, clockwise, clockwise. On the joint, counterclockwise, counterclockwise. Even if I got them wrong, it wouldn't matter because they still have to add up to 0. That says M sub CB plus M sub CD is equal to 0. There it is. But this is equation 4, and that's equation 5, and you got another equation. I called this one, I was running out of numbers, so I just said, once you do that, call it equation A. Once you do this summation, call it equation B. There's another joint down at the bottom where I can give you some information. This moment, because it's on a pin, has to be 0. There's a free body of the pin. There's the moment on the joint. And therefore, since M sub DC is equation 6, M sub CD, this has to equal to 0. I have now gifted you with 3 equations. I'm doing pretty good. How many unknowns did we have? 6? Geez, man, I'm way behind the curve at that rate. How many unknowns did we have on this structure?
3, 5.
And the average is? Very good, 4. You see, that's not an unknown. This rotation is unknown. Doot. This deflection on both ends is unknown. Boop. This rotation is unknown. Boop. And that rotation is unknown. Boop. You got 4 unknowns. If you could just give me 4 equations, I can solve for it. The only problem is all of your equations need to deal with moments on the ends, because that's the only equations I got from this method. Let's see how we're doing so far. You didn't come in on a motorcycle, did you? Oh, all right. I had some ugly things to say if you did. We're okay on this one. Look at this. This piece of information that I tried to foist off on you and make you think was good stuff deals only with moments on the ends of the members. That's good. This one's a good one. It deals only with moments. In other words, these moments refer to other equations, but those in themselves deal only with moments or deflections. And this one is good because it deals only with moments. Now I got to have another free body. So here's the one I'm going to pick. You can pick anything that you can try and make it sit still, and it's fine with me. Some people, rather than draw a new free body here, they'll take this free body, and the unknowns turn out to be this shear and this axial force, and they combine it with this free body, which this force is the same as that force, and then they get 18 equations, and they could care less because they just stick them in a computer anyway. But solving it by hand, it makes most sense just to chunk out the whole top of the structure. That leaves you with this force, which you know. It leaves you with these vertical axial forces. If you don't mind, I'm going to sum forces horizontal so they don't get in my equation. And that involves the moment. That's good. I can live with him any day. I've got an equation for him, and this moment, and two shears. So somehow I have got to relate this shear to a moment if I intend to get back to these equations. Requires another set of free bodies. There's a horizontal force. If there's a horizontal force, I don't know which way it goes. If there's a horizontal force on this member, then there's a horizontal force in the other direction on the other side of that cut face. To the right on this one, arbitrarily assumed. To the left on this one, arbitrarily assumed. Clockwise on the member, always, and therefore counterclockwise on the joint. Clockwise on the member, counterclockwise on the joint. Taking a look at this free body right here. It has no external forces applied to it. And if you would like to solve for this guy right here in terms of the applied moments, you can sum moments about that point. The axial force will drop out, the axial force will drop out, the shear won't drop out, but that's what you're trying to relate to this moment and this moment. So let me just do this one. Sum moments about D is equal to 0 is equal to. He drops out. He drops out. There's the shear at C looking towards D, multiplied 216 inches, and it's a plus, minus M sub CD, minus M sub DC. Here's the shear at CD is equal to M sub CD plus M sub DC divided by 216. Here was the original idea. The original idea was to take a joint out of the structure and make it sit still, giving us a piece of information. Take a joint out of the structure and make it sit still, and we got an equation. Take a joint out and make it sit still, and we got an equation, a piece of information. Now then, I've run out of joints. Incidentally, you might say, why didn't you take this thing down at A as a joint just like you did the others? Well, because the problem is, let me think about this. The end of the member has a clockwise, so this has a counterclockwise. His name was M sub AB, and I don't get anything. All I know is that the moment inside the floor is also M sub AB. See, this was a good one. This was 0. This was a good one. these two had to sum out to 0. But this one here just says MAB is equal to MAB. I don't get anything out of that joint. And the reason is because it didn't rotate. But you could care less why. No information comes from that joint. So I had to go whack out something else. Here's what I decided to make this piece sit still. Sum of the forces horizontals equals 0 is equal to plus 6 plus V sub BA plus V sub CD. That's what I'll call equation D. It's a beautiful equation. It definitely is going to cough up information, but the problem is V sub BA is not something I know about. Take a look at the equations. You don't see a V sub anything anywhere in there. This method just doesn't cough those up. Therefore, I had to relate these two numbers to the moments that I have equations for. Here is the sum of the moments about D. This is the one I did right here. Here it is. Sum of the moments, MCD plus MDC over 216. Here is your sum of your moments about point A on this piece to relate that shear to these people for which I have some information. Plug those two shears into equation D, and you have 4 pieces of information that you can solve for all the moments. Fun? Nah, no. Better than nothing? Yeah, better than nothing. Better than consistent distortions or the flexibility methods we've been using? I don't know. This part was sure easy. You just blindly write them down.
Once you write those equations down, what keeps you from solving for all you know? Are there too many?
Yeah.
How many were there?
All right, count them. First off, you know, some of these things have got some kind of on the way to get there.
You don't know what those moments are, right?
You don't know the moments and you don't know the thetas.
No.
And since we don't know the moments and we don't know the thetas, we in effect have 1. Now, I wouldn't count that as an unknown because that really, we know that. That's a 0. And I don't know if I ever really wrote that down, but you can be sure I would have written it down someday. Theta sub A is a 0. And theta sub A is a 0. So there's 1 unknown, that's known. 2, 3, you already counted that. That's known. You already counted that. So thus far we have 1, 2, 3 unknowns, 4 unknowns. I counted that. And I guess that's all. You have 4 unknowns in all.
So shouldn't you be able to solve them with 6 equations?
No. Excuse me, and the moments are unknown too. So when you say you have M sub AB, and I counted it, I forgot to count this guy. So you got to count him.
Oh, M sub AB is the same as M sub BA.
It is not. It's on the other end of the member.
Oh, okay.
Sadly, it's the guy 144 inches down the road. And then you say, well, wait a minute, maybe M sub BA is equal to M sub BC. I think you're right, I think it is, but that's one of the equations that we used to relate those moments. All right. 5. By flexibility. Are consistent distortions. You would draw the structure. You would admit that you couldn't solve it because it is statically indeterminate to how many degrees? 2 is correct. That'd make a good quiz problem. You just see 10 of these things and ask you how many degrees of indeterminacy does that structure have. Why is 2? Because if you release the vertical unknown here and you release the horizontal unknown here, it turns into a bent cantilever beam. Cantilever beams hold up things nicely in any direction. Therefore, it's 2 degrees indeterminate. You would sketch for me the deflected shape. Then you would come down and redraw the structure. The released structure, the primary structure, the structure that you can now analyze, and you couldn't analyze this one because you had an R1 and an R2 and an R3 and an R4 and an R5. Now that you took off R1 and R2, you can analyze it. Here's the moment diagram for that case. Drawn on the tension side. Oh, thank you, thank you, thank you. After a while, you get inured. You just get so used to it, you don't listen. How big is this moment right here? Lane. Lane showed up finally. Lane, how much moment is there right here? Oh, it's not Lane? He's sitting in Lane's chair. Oh. Yeah, sorry. You did indeed. Alan? No, I'm sorry. Hunter? He says yes. Does everybody agree? I can't pick on you. I mean, I'd rather you come for the last 10 minutes of class. You'll learn something. You won't learn much, but you'll learn something. Carol?
What's the length?
Very good question. 10 feet. Wait, I'm sorry. No fair. I can't just start making up numbers now. This is our structure. But that's a good point. It's 144 inches, 180 inches. It's 144 inches long. It's 180 inches long. And it was 216 inches long. So the length is 180 inches. Did you give me an answer and I just didn't hear it? 15? That sounds like 42. What's the answer to the universe? I forget. 42, okay. All right. Could be 15, I guess. Where'd you get that from? Carol. Is that who I asked to do this? It's 15, all right.
Well, 180 divided by 12 because it's in inches.
Okay.
It's 1 kip per feet.
Okay, 1 kip per foot times 15. That means it's 15 kips worth of load.
I think it's 112.5.
The highest point is 15.
This, you think, is 15 kip feet high? I mean, you got a lot of support here. A lot of people either don't know or agree. Getman?
Yeah, I think it's 112.5 feet.
112.5 kip feet. You really should be able to solve for the moment at that point. Now, I'm not just picking on Carol, I'm picking for everybody else, picking on everybody else who didn't give me a number. I don't know if that's right or not. Here's what it looks like, though. It's 1 kip per foot across here. That's 1 kip per foot. And the base is, we decided it was 15 feet. And so the area under here that's 15 just by itself. And the centroid of that is 7.5 feet over. So it looks to me like it ought to be 15 kips times 7.5. Is that what you gave me here? All right. And what is the moment in the middle? King. Howdy, my foot. What is the moment in the middle? How long is in the middle?
7.5 feet.
How tall is that load?
1.
What is 1 times 7.5? And if you multiply the load now under the diagram from at where you cut it times the distance to its centroid, how far is its centroid from the cut point? Okay, and you multiply that times the load, and you got what? 28 point. Thank you. All right. Well, I'm gonna just let you guys hash it out here, because that's, I can flunk you, and not even blame it on me if you can't find the moment in a beam like that. That's your 305 prof. It was obviously an idiot. Who did you have? Did you have me? Oh, that's not nice. How many of you had me for 305? Raise your hands. Well, I'm proud to say I didn't. Yes, that's true. All right. Why am I getting the moment in the middle of that parabola? So use volume integrals, so I don't have to write an equation for that doggone thing and integrate it from one end to the other between 0 and 15 and all that stuff. Yeah. All right, this does turn the corner, Getman, and is 112.5 on the other side of that joint. Why? Because there's no external moment applied at that point. That's correct. And then the moment diagram gets bigger, and by dang, you ought to be able to tell me what the value is of that moment on that end. The moment on that end ought to be 112.5 plus 6 times 12. Final answer is how much? 188. 184.5. Thank you. 184.5 kip feet. All right. Now, you guys back there, you can talk all day long when I see you doing this, because I can't get it across to him, and you probably can. When I see you back there talking, doing this, then I get on your case. All right, that's M0. The next thing you would do is you would ask yourself, who do I need to combine M0 with in order to find these reactions? You'd say, well, I'd show you a deflected shape of the structure. Under the action of the loads. This is the moment diagram that goes with that case. Here is the deflected shape. And I have no idea if I have shown that properly. I don't know if it really ends up moving to the right, up, down, left, rotating clockwise, counterclockwise. I don't care. I would call that number right there the deflection in the number 2 direction. And I would call this the deflection in the number 1 direction due to the real loads that are applied to the structure. And that means I need some unit loads in order to solve for these. Here's a unit load in the number 1 direction. And you ought to be able to do it. I hear you. I've been drawing my moment diagrams on the tension side, and therefore I've got to do the same thing now. The moment right here at the top is 1 times, I got everything in inches here, we're still going to have to convert that someday. How tall was that thing in feet? Him again. There we go, 18 feet. That number is 18 kip 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 feet. What is this number right here? I really think there's probably a lot of practice with sheer moment, just moment diagrams going to be required to get you through this mess. How much moment is there, Nelson?
Would there be 6?
I think you're probably right, because if you sum moments about this point, this guy is 18 minus 12, that's 6 feet away, and therefore it is correct. Kip feet. And that's the thing, 90% of you probably already know these numbers, you're just not responding. You figure the fewer responses, the less I make you learn. All right, that is M sub Q due to a unit load in the number 1 direction. To get delta 1, 0, you will combine either using volume integrals, M sub P due to the real loads, M sub Q due to the 1 direction, dx over EI. Here's the moment diagram for a unit load in the number 2 direction on the tension side. That is M sub Q due to a unit load in the number 2 direction. To get delta 2, 0, you'll integrate M sub P 0, M sub Q 2 dx over EI, or you'll use volume integrals. To get delta 1, 1, you'll integrate what? I'm watching the time. Green. Yeah, look at them look at each other. Green in the green shirt. No. No? Green. How would you get delta 1, 1? Green in the white shirt. Guy sitting next to green in the white shirt. Guy in a green shirt. No, no. Anybody, please. Getman, let's go.
Integrate that with itself.
That's exactly right. M sub q1 with m sub q1 dx over ei. Delta 2, 1 is equal to the integral of m sub q2 m sub q1 dx over ei. You've already got everything you need. Delta 2, delta 1, 2 is equal to delta 2, 1. By what law? And delta 2, 2 is the integral of m sub q2, m sub q2. Oh, wait, come on. No, you're right. It's time to go.
I have a question.
Incidentally, those of you who were here on time, I will give you 10 points on the pop quiz. I don't have time to take it up, but I know who you are.
Can I tell you if you're doing late or not?
No, it doesn't matter.
On this
Yes, sir.
structure, it's like a frame.
Right,
Like this and like that.
right.
There's no moment in this vertical bar, is there?
You're right. There is not.
Okay.
It just so happens.
Yeah. And on this next one, I'm not that good at frames. You have this thing.
Right.
That's kind of what it would look like.
Right.
Again, there's no moment in that vertical piece.
I don't know. Let me think. It's yeah. Well, since there are no hars, well, now wait a minute. Now, is it supported here and here?
Yeah.
No, I think there will be moments in here, and the reason
Oh, this is the release structure.
in the release
So
structure.
now there is no horizontal.
No, you're right. In the release structure, that's correct. Yes.
In this one right here, can you just
Yeah.
find the horizontal without worrying about the vertical, and then just after you find the resultant, can you just do it by statics, finding the actual?
No. And here's why. There are too many unknowns. That's page 6. Where's page 5? You see how the structure stands up nicely if you'll take both of these off?
Still be indeterminate. By
This still be indeterminate by 1 degree. Okay?
You didn't call my name. I don't know, because you went from beats and then you just skipped me.
either, but I think you just acknowledged this because there's only two.
No, I'm sorry. There were a couple of you there and I saw, and I just went on to the next
Okay.
people. I'm sorry.
Okay.
If you'd like to check, Alahar and Dietz? No, I got you here. I'm sorry.
Is that for attendance or just for? Because I got here like 3 minutes late.
Yeah, no, this is for pop quiz. We had a pop quiz at the beginning of class. Yes.
Another question on my homework.
All right, let me go ahead and turn this thing off.